This is 40 Days of Chemistry, Part 4, and I've got a good feeling about the 5 minutes this time. This is actually Part B of 9.2.5, which we previously covered in Episode 2. This time looking at medical and industrial radioisotopes. And the first thing we're going to look at is industrial uses of radioisotopes. Now, this is part of the production of materials topic, and the whole concept here is that radioisotopes are useful materials or resources, and they are produced in nuclear reactors and particle accelerators, that's what that stands for there and there, using the techniques of nuclear chemistry. So radioisotopes are produced materials that are useful. And the main use for industrial isotopes, or one of the main uses, is non-destructive testing. First of all, you can use them as a tracer in things like underground pipelines. You can inject your radioisotope into the underground pipeline, and then you can see, is there a leak? If there's extra radiation coming out above the surface, that means you don't need to dig up the pipeline to find the leaks. You can do it non-destructively. Next, you've got thickness detection, which is one of the main uses of cobalt-60. By shining or by passing the radiation through the sheet that you're trying to detect the thickness of, you can measure how much radiation comes through. The more the radiation comes through, the thinner the sheet. So you can do non-destructive testing of thickness, and that can be an automated process as well, which is very important. And finally, you've got flaw detection. Here you've got a pipe. They've put their cobalt-60 or other gamma source inside the pipe. That's going to emit gamma rays. You put detectors on the outside, which could be film. If the film is exposed in any particular one spot, say over here, that means there might be a flaw in that pipe just there. So you can detect flaws in the pipe without destructive testing. And some other main important uses of industrial radioisotopes, first of all, is sterilization. Medical equipment needs to be sterile before it can be used in case you infect the person you're using the medical equipment on, and for that they use gamma sterilization. This here is a gamma sterilizing factory. What happens is the medical equipment is brought into this conveyor belt on this side. The conveyor belt takes the medical equipment all the way through the factory. Inside this big concrete bunker you've got some gamma ray sources. The equipment is sterilized as it goes through, and then it comes back out again. It's a completely enclosed system. So sterilizing is a very important use for gamma rays or radioisotopes. Another very common use is in smoke alarms. Inside smoke alarms, inside this chamber here, you've got an americium-241 source. That's an alpha emitter. It ionizes air very readily, so as the alpha particles are coming out of this alpha source, it's ionizing the air particles here, which makes ions, which can then pass a current between two electrodes. If there's smoke in the way though, that's going to stop those alpha particles, it'll stop the current flow, and the alarm will go off. So that's industrial uses of radioisotopes. Medical uses of radioisotopes come in two main forms, but they're all about non-invasive testing. Non-invasive means you need no surgery, which is very important because you don't have the risks of infection when you get cut open. You don't have also other surgery risks such as anesthetic risks, etc., etc., etc. What we've got here is diagnosis versus treatment. Now, diagnosis, what you can do with diagnosis is you can inject a tracer inside the person's body which carries a radioisotope, and as that passes through the body emitting radiation, you can use radiation detectors to detect where that radiation is coming from. In this case, this person has bone cancer. In actual fact, this is metastasized prostate cancer. With prostate cancer, what can happen is those cancer cells can then leave the prostate and end up in the bone, causing bone cancer, and it's incredibly painful, which leads to another aspect of radioisotope use in medicine, is treatment. What they can do, they can get this isotope here, which is samarium, I think 153. They can inject that into the body, and it's preferentially taken up by the bones. And wherever these cancers are growing, it'll absorb this samarium-153, and that samarium-153 is very good at killing those cancer cells and also some of the nerve cells around that, which prevents the pain of that particular cancer. Other forms of treatment, there's iodine-131. That's taken in the form of a tablet, and that locates itself in your thyroid glands. If you've got thyroid cancer, that iodine-131 can then kill the thyroid cancer. You've got things like gamma cameras here. They have their gamma source, which could be a cobalt-60 source, inside that machine there, and that can rotate around the body, passing gamma rays through the body, preferentially to kill the tumour. Another use for cobalt-60 in particular is brachytherapy. And what that is, they put these little tiny fine needles inside your body. Each of these needles contains cobalt-60, and they can put them at the side of the tumour, and that cobalt-60 emits its beta and gamma radiation, therefore killing tumour. Just as an aside note though, I recommend you don't look up brachytherapy in Google image search, because where they put those needles and how many needles they put in, it's quite a scary thing. Now let's move on. We've got advantages and disadvantages of the use of radioisotopes. Well, let's look at advantages to industry first. What we've got here, Let's get that out of the way. They provide an automated, sensitive and precise measurements. They can analyse internal structures in a non-destructive manner. That means the item doesn't need to be cut open and destroyed to analyse the internal structure. It's quick and reliable. No power source is required for the radiation to be emitted, unlike X-rays, which require a power source. And gamma rays are highly penetrating, can be used for thick metal components. What are the advantages for medicine? So let's get that out of the way. You can cure potentially fatal cancer cells, which is therapy. Treatment of cancer can occur without the need for surgery, so you've got less infection risk. You've got diagnosis as well. Diagnosis of disease can occur once again without the need for surgery, and can diagnose disease in places which are dangerous to physically examine, such as the brain and the heart. Disadvantages though, let's get rid of that big box there. Look at the disadvantages. There's a whole range of disadvantages. First of all, as we know, ionizing radiation can cause harm to tissues. We saw that in the previous episode on radioisotopes. It can damage DNA and therefore lead to cancer formation. There's always a risk of overexposure to healthy tissue, so you might cause damage to healthy tissue. There's a risk to the doctors, nurses and technicians who handle the isotopes. You've got the issue of radioactive waste. Once you've used the isotope, it's going to have radioactive daughter products which need to be disposed of carefully or stored carefully because they're themselves radioactive. And then you've got the terrorism risk as well. Terrorists would like to get their hands on radioactive materials to make what we call dirty bombs. So there's an issue with security of radioactive waste. There are some things we can do or precautions we can take to overcome some of those disadvantages. Things like using lead aprons, using badges, using low half-life materials. You can pause this slide and read them if you wish. Let's look at cobalt-60 though as our main case study for isotope industry. Now, cobalt-60 is produced in a nuclear reactor by neutron irradiation of cobalt-59. We might have seen this in the previous slide, but essentially what you've got is inside the nuclear reactor, you've got a source of neutrons. That is our source of neutrons, nuclear reactors. You fire those neutrons into otherwise stable cobalt-59 to become that beta-emitting cobalt-60, which has excess neutrons, therefore it's a beta emitter. Once you've made cobalt-60, it's got a half-life of about 5.3 years. It decays by beta emission, but it also emits 2 gamma rays at the same time. So it's very useful because it emits these very powerful gamma rays as well as beta particles as well. Uses and detection. What do we use this cobalt-60 for, and how is its radiation detected? It's used for radiation of food. It's used for flaw detection, thickness detection in rolled products. As you can see up here, this picture here shows a rolling situation. You've got some sort of steel or something being rolled. You've got your cobalt-60 gamma source up here. It's passing radiation through the sample. It's got a detection set up and a feedback loop to tell the rollers to either press harder or don't press as hard depending on how much radiation is getting through. You've got sterilization of medical equipment, and a very important use is automated filling of containers. There's a picture up here which I'll try and show you if I can bring it up on the screen. Well, maybe it's not going to let me today. Here we go. This picture here, I'll bring it across. Automated filling doesn't sound that exciting, but it's very important for efficient industry. It means that you can have a industrial line, such as a bottle filling line, and what happens is the machine starts filling up the bottle. As soon as the liquid level reaches the top, the gamma beam source is stopped or partially stopped. That's detected automatically, and therefore the filling stops and the next container moves along. It's very important for industrial efficiency, as it says down here. Useful nuclear properties. What are the useful nuclear properties of cobalt-60? It's got a relatively long half-life, doesn't need to be replaced very often, so you've got less handling required. The gamma radiation produces high energy, so therefore it's effective at killing microorganisms, and being gamma, it's got high penetration power, which means you can measure the thickness of things like steel. What are its useful chemical properties? See, this is a chemical course. First of all, it's a relatively inert, and it's also a solid metal, so it's not very chemically reactive. If spilt, it's easy to contain, unlike some other isotopes such as cesium-137, which could be used to produce gamma rays as well. Let's look at technetium-99 in medicine. How is it made? Well, you start off by making molybdenum-99 first. And molybdenum-99 can be made by neutron irradiation of molybdenum-98, but more often than not, it's used by one of the fission daughter products, or produced as one of the fission daughter products of uranium-235 fission. And I've left that for you to do because you need some practice at those sort of things. Now, molybdenum-99's got a half-life of 66.5 hours, and it's a beta emitter, and that can therefore be transported a long way from the Sydney ANSTO nuclear reactor all over Australia and the Oceania. So you can take this with 99 a long way, and once it decays by beta emission. It's a beta emitter. When it decays, it produces technetium-99M. M means metastable. It's got an unstable nucleus containing too much energy, so when it decays, it's going to be a gamma emitter, as it says down the bottom. Now, technetium-99 has got a half-life of 6 hours. That's not enough to transport, but luckily the parent, the molybdenum-99, can be transported because it's got a 66.5 hour half-life. So what do we do with the technetium-99 once we've got it? Well, let's have a look. Uses and detection. It's used mainly as a tracer. It can be combined with a range of specifically tailored bioactive molecules and used as a tracer. They're taken into the body, they migrate to sites of interest such as the bone, the heart, the lungs, and the radiation emitted can be detected by a gamma camera. Now, what is a radioactive tracer? It's also called a radioactive label. It's a substance containing a radioisotope. They're used to measure the movement of a substance through a system by monitoring the emitted radiation. And as an example here, this isn't the right bioactive molecule, but this is an example bioactive molecule up there. You've got the T99 in the middle, you've got quite a complicated organic molecule around the outside, and that will be taken to a certain part of the body. One example use is detecting blood flow in the heart. For example, this is a T99 scan of blood flowing through one of the coronary arteries, and as it's detected there's a flaw in the wall of the coronary artery there. So it's very important for this non-invasive diagnosis. What are its useful nuclear properties? Let's have a quick look at those. In fact, it's got a very short half-life, means it's got rapid gamma emission, which means you can have quick scanning, which minimizes dose to the patient. Low energy gamma emission makes it useful to be very safe, a low chance of ionization to the patient. The 66.5 hour half-life of the parent means that it can be transported from the reactor to wherever it's needed. And what are the useful chemical properties, seeing this is a chemistry course? First of all, the very fact that the T99 can be tagged to many useful bioactive molecules makes it useful. And second of all, the body has no need for T99, and therefore it's quickly excreted from the body, causing no long-term problems. And that is the end of part 4 of chemistry in 40 days.